So we're going to look at a similar scenario, but with a radical function. So with this function, it's giving us a framework of, we're going to have some input, and what we'll do is take the square root of 3 times that input plus 1, all underneath that radical. So if I want to look at b of 8, then what I would do is take square root 3 times 8 plus 1. So just plugging the value in. So this would be a square root of 24 plus 1, which is a square root of 25, which is positive 5. Plugging in negative 2, we would do the same thing, but now we're taking square root of 3 times negative 2 plus 1, which would be the square root of negative 6 plus 1, which is the square root of negative 5, and we cannot take even roots of negative numbers. So this does not exist. So something that's going to come up with our radical functions is we need to keep in mind domain. Like if we look at the graph of this function, what you'll see is that our domain's limited, and it's limited by that fact that we can't take the square root of negative numbers. We can take the square root of 0 and anything larger, but negative numbers aren't allowed. So we have this limitation to what values we can plug into this function. So sometimes we might get values where it does not exist. Okay, in this next piece, what we're going to plug in is this whole x plus 1 is going to be our input. So we'll be taking the square root 3 times, and then in those parentheses we'll put that entire x plus 1, and then plus 1 on the outside from our function. So we'll distribute that 3 in, so that's the same thing as 3x plus 3, and then we still have that plus 1 at the end there. So this is going to be the same thing as the square root of 3x plus 4. So that's what it will look like if we have x plus 1 as our input. If we have plus 1 on the outside of the function, so b of x and then plus 1, what that will look like is we'll just copy down b of x, which was the square root of 3x plus 1. And then with this plus 1 on the outside, we'll just put that on the outside. So it would go outside of the radical piece of our function. Plugging in x squared, so we're going to have the square root, 3, and then times, and then in those parentheses we'll put x squared, and then we'll have a plus 1. So that's the same thing as the square root of 3x squared plus 1. If the square is on the outside of the function, then what this will look like is, if I draw those parentheses with my exponent of 2 on the outside, the input that I want in there is that entire b of x function. So within those parentheses, I'm going to put that square root of 3x plus 1. Now, when you have a root and an exponent, and they're the same level, like this is a square root, and that's a squared exponent, they cancel each other out. So what we'll have is just what's inside of the radical, so that'll simplify to just 3x plus 1. So that's the difference of having our square on the inside and affecting the input of the value versus the square on the outside affecting the output of our value. Okay, let's look at some examples where we're solving. So b of x, so that's our square root of 3x plus 1, equals negative 1. Now in solving radical functions, what we want to do is get rid of the radical. Our first step would be to isolate the radical on one side of the equation, which it already is. And then what we want to do is to get rid of that root, we're going to use exponents. So what I'm going to do is square both sides of the equation. So in doing that, the root and the exponent cancel each other out, so we're just left with 3x plus 1 on the left-hand side. And then negative 1 squared would leave us with a positive 1. Then I'll subtract 1 from both sides, so that'll leave us with 0. And then divide 3 from both sides, so we're getting x equals 0 out. Now, in these equations where we're solving, but we know we have this limited domain, we should always check our answer. So let's see what happens when we plug in x equals 0. So if I take the square root of 3 times 0 plus 1, what should happen is I get negative 1 out, but what you'll see is this will simplify to a square root of 0 plus 1, so it's a square root of 1. I'm getting a positive 1 out, which is not equal to negative 1. So what that tells me is that this solution actually doesn't work. We got an extraneous solution, and we don't have any other options, so that means there is no solution. So what that looks like graphically, if we have our radical function, so that red line is our 3x plus 1, if I graph the line y equals negative 1 to see where they intersect, you can see they never intersect. We got this extra solution where it's kind of hard to imagine, but if this was like a parabola on its side and it continued on, then we would cross. But if we continued on like a quadratic, then it would no longer be a function because we would fail that vertical line test. So when we have these root functions, we only have this top part. So because they never intersect, that would show that there's no solution. Let's look at our next case here. So we're having our function equal 2x. So square root 3x plus 1 equals 2x. We have our radical all isolated on one side of the equation, so we're going to square both sides. So on the left-hand side, the radical and the exponent would cancel out, so we just have our 3x plus 1. 2x squared should simplify to 4x squared. Now I can see, solving this, I have something that's quadratic. So I want to get 0 on one side of the equation. So with that, I'm going to keep my 4x squared positive, so I'm going to keep that on the right-hand side, but I'm going to subtract 3x from both sides, subtract 1 from both sides. You can use the AC method. In fact, we haven't done that in a while, so let's go ahead and check the AC method. But if you can find this with the trial and error, that works great too. So I would take 4 times negative 1. So I want to look at the possibilities for negative 4. That would add up to negative 3. So I know it's going to be 1 and 4 together, so it's either negative 1 and positive 4 or positive 1 and negative 4. And it's going to be the 1 and negative 4. So let's go through this process. So I'm going to split up that middle term where I had negative 3x. I'm going to split that into 2 terms where I have a positive 1x and a minus 4x. And I still have that minus 1 at the end. And we're going to use grouping. So I'm going to factor out an x on the left-hand side, so that'll leave me with 4x plus 1. On the right-hand side, I have a negative I can factor out, so that'll leave me with 4x plus 1. So factoring this, we should get 4x plus 1 as a factor and x minus 1 as a factor. And then continuing our solving, we're going to have 4x plus 1 equals 0. So solving that, we'll have 4x equals negative 1, divide by 4. So x can be a negative 1/4. X minus 1 equals 0. Add 1 to both sides, so we can have x equals positive 1. Now again, we need to check our answers. So checking, we would plug these in to the original form. So what we could do is go to our scientific calculator and plug in the square root of 3 times a negative 1/4. And then plus 1. And that works great. But we should make sure that it equals the other side of the equation, which is where we're taking 2 times x, so 2 times negative 1/4. And what we now see is we're getting different values. So even though both sides are defined, they're coming out with different answers. So that means that negative 1/4 does not work. Let's, while we're here, check 1, because I can just kind of substitute it in. So positive 1, and we see that positive 1 is going to balance both sides of the equation. So that x equals negative 1/4 is an extraneous solution, but the x equals positive 1 works. And just to look at the graph real quick so you can see how that works. If I graph the line y equals 2x, I can see I have this intersection point where x equals positive 1. So there's our answer that we found. but we have this extraneous solution where our graph isn't occurring, because if our graph continued, then it wouldn't actually be a function. So that's how we would work with radical functions.